Welcome to the spring lecture of the 2025-26 Distinguished Faculty Series. My name is Fad Abdel Khaliq. I'm provost, and I want to again thank you and welcome you to this lecture, the Distinguished Faculty Lecture. Today, the title of this lecture is Keeping the World Connected, Building a Faster, Smarter, and Greener Internet, which will be presented by Dr. Ramesh Sitaraman, our distinguished professor in the Manning College of Information and Computer Science. So if you just indulge me for a minute, the way this is going to work, I'm going to soon invite Dean Marzullo to join us here to introduce our distinguished speaker. He'll deliver his lecture. We're going to have time for Q&A, and then our Chancellor Javier Reyes, will present our distinguished speaker with the campus' highest recognition, which is the Chancellor's Medal, then maybe a few photos for legacy's sake, and then we all can go down to the first floor for a reception, high-quality food prepared by the best dining services in the nation. So that's how we're going to run, and please always recall that we videotape this lecture, and it's going to be available on the website. So after viewing it, if you want to invite others to come and watch the great work, please do. It now is my privilege to introduce Dean Keith Marzullo, a renowned computer scientist, educator, and policy leader with a passion for fostering interdisciplinary collaboration. He's been on campus effectively for a few months, but you already feel like a veteran of this campus, Keith, so always good to see you. Dean Marzullo was appointed as Dean of the Robert and Donna Manning College of Information and Computer Science just in July of 2025, and I would like to invite Keith here to present our speaker.
Good afternoon, and thank you, Provost Abdel Khaliq. So it is my honor to introduce this evening's distinguished faculty lecture speaker, Professor Ramesh Sitaraman. This recognition reflects not only the extraordinary impact of the research, but also his deep and sustained contributions to the university and to the broader field of computer science. I'd first like to acknowledge and thank Ramesh for his leadership here at the University of Massachusetts Amherst. He is currently wrapping up 4 years as the Associate Dean of Educational Programs and Teaching in the Manning College. In this role, he oversees operations, curriculum, academic support, and strategic planning for programs serving more than 2,300 undergraduate and graduate students. In my first months here as Dean, he has been a wonderful partner, thoughtful, steady, and deeply committed to academic excellence and to strengthening and evolving our academic programs for the future. Thank you very much. Professor Sitaraman's commitment to teaching has been the foundation of his work as Associate Dean. Alumni frequently tell me how much they appreciated Professor Sitaraman. He is widely known for his innovative teaching of algorithms, where he brings the Socratic method to life in the classroom, challenging students to think rigorously and independently. He's a recipient of the Distinguished Teaching Award, the highest teaching honor on this campus, as well as the College Outstanding Teaching Award. He also led the creation of our informatics program, which is an interdisciplinary undergraduate major that applies a computational lens to fields across the university. This initiative has expanded access to computing and has broadened its impact. But this evening, we're here to celebrate his research. Today, the internet is so deeply embedded in our lives that we rarely stop to consider how it works or how fragile it once was. At the turn of the century, 25 years ago, the internet was a patchwork of networks plagued by failures, strained capacity, and poor performance. Over the past 25 years, Professor Sitaraman's work helped transform that early, unreliable system into the fast, resilient, dependable global infrastructure that we now can depend on for communication, commerce, education, and innovation. As principal architect of Akamai, he helped create the world's first major content delivery network and the first edge computing services. These were the pioneering technologies that now deliver much of the world's web content, video, and online applications to billions of users. His work has made it possible for web pages to load quickly and videos to stream smoothly, even the most remote corners of the world. During moments of global crisis, including 9/11 and the COVID-19 pandemic, the systems he helped build enabled the internet to withstand unprecedented surges in traffic and to keep the world connected. His impacts have been recognized at the highest levels. Professor Sitaraman is a fellow of the Association for Computing Machinery, the IEEE, and the American Association for the Advancement of Science. He has received the ACM SIGCOMM Networking Systems Award, the ACM IMC Test of Time Award, the IEEE William R. Bennett Prize, and just last week, the IEEE Infocom Test of Time Award. These, among with numerous other honors, they all honor his work that has fundamentally shaped how the modern internet operates today. The arc of his career began with a simple but profound question: how do we make networks reliable? He received his Bachelor's of Technology in Electrical Engineering from the Indian Institute of Technology in Madras, where he was later named as a distinguished alum. He went on to earn his PhD in Computer Science from Princeton University, where in 1993 he wrote a groundbreaking dissertation on network reliability. This work foreshadowed much of what would follow. Now, as artificial intelligence reshapes the digital landscape, Professor Sitaraman is turning his attention to the next great challenge: delivering AI-enabled services to billions of people worldwide while addressing the rising energy demands of massive data centers. His vision of a more sustainable internet, one that is only faster and smarter, but also powered by clean, renewable energy. Please join me in welcoming distinguished Professor Ramesh Sitaraman for his lecture titled "Keeping the World Connected, Building a Faster, Smarter, and Greener Internet."
Thank you, Dean Marzullo. I'm really, really excited to be here, and I want to thank you all for braving the weather and coming up here. As the provost said, it means that you really want to be here. So I'm really excited to talk about this topic, the internet. It's something that has been my obsession for more than 25 years. But before we really even go there, I want to actually do a little thought experiment. Suppose we were to turn off the internet for the next week. Just turn it off, starting now. What is it that you couldn't do? I want you to raise your hand if there's something in the list that you would have wanted to do but you couldn't do. Okay? Connect with family and friends. Read the news, watch entertainment, buy stuff, pay for stuff. I don't carry cash anymore, and drive without a GPS. Maybe that's just for me. I mean, I can't find a way without GPS. I see a lot of hands up here, and if you actually look at the stats, it's pretty clear. There are 6 billion people on the internet. That's something like 70% of the world's population. Each person spends a lot of time on the internet, and it's something that you cannot live without. But I want to take you back to a time, some 25 to 30 years ago, when if I had asked the same questions, the answers would have been very different, right? So I want to take you back to the internet of the late 1990s. This is a time where, a few people used the internet. They thought it was a nice-to-have thing, but it wasn't like, defining your life in any way. So I want to, in this talk, I want to give you a sketch of starting from here to where we are now and where we are going into the future, talking about the internet and also my research as a part of that. So what did the internet look like way back when? It was slow, it was unreliable, and it won't scale. Now, this is an actual screenshot from way back then when someone was trying to download something and, could take 39, and it really could, actually. So, but people had a lot of hopes for the internet, even back in the late 90s. They thought it's going to solve all the world's problems. And one of the defining moments is the Victoria's Secret fashion show, which used to be in person, but they decided suddenly that it's going to be online on the web. So they took this ad in the Super Bowl, 1999 ad, which pretty much went like this. The Broncos and Falcons were playing. They said, they'll not be there, but the show will be live in 72 hours. They announced that. And guess what happened? Lots of people landed up. They all wanted to see it online. They all landed up. They were only streaming at some really small, today it's like dial-up, like 28.8 kilobits per second. That's really what the connection was. but it just broke the internet. But of course, that's nothing like bad publicity. They actually came out okay from that. So that was really the state of the internet. There were lots of hopes, but that really wasn't. It really didn't work. And people started to give up on the internet at that point. People wrote things like, "The internet is not your TV. It cannot do the things that that you would want it to do," and so on and so forth. So the hype was being decreased a bit. So I want to say a little bit about what I was doing in the 90s. I was interested in networks for a long time, and communication networks. My father actually worked for the post office in India, the Indian Postal Service. And I was always very intrigued by how you can drop a piece of mail in one place and how it got to the other place. And I was always interested in networks. So when I got to college to do my PhD, I said, you know what, I want to think about networks. I want to see how we can route on networks. And how to, if things fail, how do you tolerate those failures? So that's what my PhD thesis was about. How to actually, the theory of how to tolerate failures using something called overlays. Okay, so for example, here is a communication network. There is A communicating to B, and there is C communicating to D. And you could ask, what happens if something fails, right? So let's say that node there fails, right? You would have to route around it. So this is called overlay routing, where you just switch the paths around so that you avoid the congestion of the failure. Okay? So my thesis was about how to do these things in an algorithmically efficient way so that you don't have a major performance degradation. You see that some routes may get longer, and things may get more congested. So how do you do that in an efficient way? That was my thesis. And I was very thankful when UMass hired me as a theoretician here. In those days, theory person means that, whatever you say probably will never work. Anyway, I was really happy, and I was actually happily building this theory. So I built this theory about how networks could work, but there wasn't a network that I could use the theory on till the internet came along. And that's where in the late 90s, around 1999, the internet came along. It seemed to be important. It seemed like people wanted to make it more efficient. People wanted to make it more reliable. And so I said, well, maybe the theory can be put into practice. So I left academia for a few years. My PhD mentors actually started Akamai Technologies, a company that's in the Boston area. And I joined them. These are the people I'd worked on the theory on. And I said, let's see if this thing could work. And so, I spent quite some time in industry trying to build internet content delivery to see if we can actually cure some of the problems that the internet had. I really won't go into my startup stories, but those years were really one of the most eventful years of my life. The internet bubble was raging. People thought that we came from heaven because we were trying to solve all these problems on the internet. Then there was 9/11, and then the bubble burst. And then all of a sudden, it wasn't clear whether we would even succeed. I mean, they said, you have 3 months to just close up shop. And then we came back and we recovered. So there are a lot of events and stories there. I really wouldn't go into that now. But I want to actually talk a bit about what is it that we did to make the internet work more efficiently. Okay, so that's really, I'm going to actually do this in 3 parts. My title had 3 things in it: making it faster, making it smarter, and making it greener. So those are the 3 things I want to talk about. Making it faster is really coming up with this new kind of network called content delivery networks. Making it smarter has to do with edge computing and edge AI. And then I'll talk about making it greener, which is one of the most pressing problems in the internet today. So let's start with the first part of it. How do you make this faster? How do you make the internet faster? To really understand that, we first need to look at why is it slow in the first place, right? Why is it unreliable in the first place? Why doesn't it scale in the first place, right? That's the first thing we need to understand. So the internet actually looks very simple from the outside, right? So I've drawn a very simple picture here. You have all the services that you want to access on the left. You might be going to a web page. You might be going to video. You might be accessing an app. And you have stuff on the right side. These are the users that want to access all of these things. And the internet is there right in the middle to connect what's on the left, what's on the right. So what can be so complex about that, right? But when you look at it inside, it's actually pretty complex. The fact of the matter is that the internet is not one network. It's actually 80,000 independent networks. There's no one central thing that governs the internet. So there are all these different kinds of things managed independently that collaborate in some suboptimal way to do things. So that's really it's that way by design, actually. And so if you actually route a packet, let's say, the way information travels on the internet is through packets, right? So, if you access the web page, you break up the web page into small packets, and then you just route it on the internet, right, from point A to point B. So if you route something, let's say somebody is accessing the thing on the top here, this one here, packets get routed from this server to this user out here, right? And it goes through all of these different networks to go from left to right. And these networks, as I said, are not particularly well coordinated in terms of performance. So this path could be, it's not the fastest path for sure. It could be pretty long. The latency could be pretty high. Okay? And there can also be failures. So for example, it could fail on the first mile, like here, or the packet could get dropped when you're actually crossing between networks. Those are called peering points. So this is the way the internet is built. We call this a network without any guaranteed service, okay? And it's sort of a little bit like our postal service, actually. You drop the mail, it will get to the other end. We can't say exactly when. It might get lost also, right? That's the way it is. Okay, so this is one problem, right? So the other problem is that if there is a flash crowd or a hotspot, I gave you the example of Victoria's Secret, right? What really happened there? Everybody was going to the same place. And if that happens, this is what happens. So you have all these users all going to this one place where they want access, and the internet can get extremely congested going there. And things could break. These are really the two main problems why the internet does not work as is. And this is the problem that we were trying to solve by doing something different. Okay? I want to do this a little bit Socratically. Here's a web page. This is the CNN web page that I took a snapshot of earlier today. I want to ask, how do you speed up this web page? This web page sits in some CNN server somewhere else, let's say in Atlanta, right? We are sitting in Amherst and we want to download this web page, right? How do you make this fast? Now, if you just do the obvious thing, you go all the way to Atlanta and you get all the web page and all the images, right? That may not work very well because the internet, the way it's designed, it's not optimized for performance, right? So here is the basic idea. This is the basic idea of CDNs. The basic idea is that the first thing you note is that a lot of things on this page don't change. It's called static content, right? For example, the CNN logo doesn't change at all, right? This is basically an image of some sort. It's fixed. These are all like on-demand videos. They're all fixed. They're all static content, right? There's no reason for you to get the static content all the way from the servers in Atlanta, right? You can, in fact, have a server at UMass that stores all this content. And anyone from UMass accessing it just gets it from the server nearby. That server is what we call an edge server. And I'm not lying here. There is actually edge servers on this campus. If you actually go to CNN, you're probably getting it from here, not from Atlanta. Okay? But this doesn't work for everything, right? So think about this case. This live video there, right? And the web page itself, right? The web page itself has different news stories. It's not static, right? This is dynamic content. So this is stuff that you have to get from elsewhere. And we have this idea called overlay routing to get it faster. So these are really the ingredients of the solution, right? So when we came up with these ingredients, we said, okay, let's try and actually build the system, right? So 3 steps to building the system. The first step actually is the most difficult one. You want to deploy servers where users are, right? And this is what I call an edge. I'll be using the word edge quite a bit. Edge is a collection of servers that are close to users. It's different from a cloud. A cloud is, maybe, tens of locations of servers, right? An edge is something where it's a set of servers that are really close to you. And if you really want to be close to everybody in the world, you're going to need hundreds of thousands of servers. So in a modern CDN, it may have something like 500,000 servers, okay? And you also need to be in thousands of locations. You need to be in every country. You need to be in every network. So really, an edge, you would have thousands of locations. It'll be in pretty much any country. It'll be close to most users. Like, there are edge servers right here on the UMass campus. The first thing is you need to deploy this, right? Of course, it takes a lot of money to do it. You have to do it gradually, okay? And once you've deployed it, you can play the tricks that I told you, right? You take all the static content and you cache it at the edge so that users never need to go far away on the internet to get them, right? And then the other idea that comes in is overlay routing. When you have content that changes, you need a fast way to go from wherever the content sits to wherever the user is, right? So we developed a whole bunch of algorithms that finds the shortest path on the internet. It's basically like GPS for the internet. So essentially, it takes the weather of the internet, which is which paths are congested, what is the latency in all the paths on the internet, and then it sucks all of that up and creates something like a GPS so that the packets can actually follow the best way to go from point A to point B. So this, at a very high level, this basically describes what a CDN is, okay? So we successfully built this, and the approach actually worked. This is one of the earliest measurements of the CDN that we built. So we are measuring how much time it takes to download an object using the CDN technology and not using it. And you can see what the internet used to look like without CDNs in those days. It's a pretty small object, but you can see that it takes 10 seconds, 5 seconds sometimes. But the CDN downloads are pretty small. It takes very little time. And the reason why it takes very little time is it's coming from an edge that's close to you. Let me also quickly mention why you don't have any scalability problems with CDNs. Remember, I told you that if lots of people want to see the same thing, you have a problem because they're all going to the same place. With CDNs, you have such a huge edge that you can just move the load around. If you have 500,000 servers and all of a sudden something becomes extremely important, you can just spread it onto the other edge servers. And you can absorb the extra load using these edge servers. And that's what gives it the scalability. So we had actually built this, but in those days, the internet was still not considered a must-have in the late 90s. And there were a couple of things that actually changed that attitude around. And if you think that the internet is not a must-have, then you're probably not that interested in CDNs because it speeds up the internet, but the internet itself is not that important, right? So there are a couple of things that actually changed the thinking around. And the first thing is the 2000 presidential election. I don't know, some of you probably remember that. The outcome of the election was uncertain. And when the outcome was announced, everybody went to the internet to see what it was. And it pretty much melted most of the media websites. But it turned out that Washington Post was an early CDN adopter. They actually implemented CDNs before people normally did. And we were able to actually show that they were actually able to serve millions of users, something more like 20 million users, without actually melting down. And we also computed that if they hadn't used something, they would have probably not gone past this red bar here. So this was really a real-world test for whether this thing worked or not. And in the case of Washington Post, it worked. And it started to change the mood of the public in terms of what the internet was. And it's really summed up very nicely in a newspaper article that came out in that period, which basically said, in a short span of time, internet information feeds have come to rival the more traditional news outlets of radio and television as the fastest way to access reliable information during breaking news events. So the 2000 election was really a turning point in terms of how people viewed the internet, and in terms of getting the news and so on. There's one more thing, inflection point that I want to talk about. It's also a very personal thing because I think 9/11 was one of sort of the worst days of my life. I got up in the morning, I went into work, and I saw a huge bunch of people crowding around. And they were all watching the video of the planes flying into the building. And then one of us said, you know what? Our colleague, so Danny Lewin was a friend of mine and a colleague of mine, and Naka, my co-founder. We said, Danny was on that plane. Danny was on American Airlines 11. And immediately we knew that he had passed away. And we were all in a huge amount of panic. We didn't know what to do because he was very, very close, and in fact, I'd spent a lot of time with him the previous week, and so we didn't know what to do. But then something else happened. The phone started to ring. People are accessing the internet on 9/11. People are going to the American Airlines website to see what the passenger list was. And most of those sites are just melting down. The media sites are melting down. And they all called in and said, could we actually use the CDN services now? And so we spent the rest of the day on 9/11. I still can't erase that memory. Just working, trying to get all of those people onto the CDN technology so that they can actually, people can actually access those websites. And I would say that 9/11 was really a turning point of how the internet is viewed. People started at that point to really look at the internet as something that they really, really need to have. So since those days, CDN technology is very widely deployed. Pretty much all the major events that you see are served by CDNs. I just put down some of those. Some of the early events, Steve Jobs' keynote was one of the early events for live streaming. You can see a whole bunch of other things, like the Super Bowl back in 2012, FIFA World Cup. And you can see that the events just keep getting bigger and bigger. And the edge capacity of the CDNs also keep growing bigger and bigger. And if you look at it today, pretty much everything on the internet, 75% of the internet actually goes on CDNs, including things like www.umass.edu or www.whitehouse.gov, all of those things really under the covers. You don't see it, but when you actually go and access it, underneath the covers, the CDN technology is actually moving the content to you. This is something I was very happy about, just a few years ago. You remember COVID happened, and people just shifted work from being here to working from home. And that put an enormous amount of stress on the internet. And you can see that this was March 13, 2020 is when the COVID emergency was declared. And you can see that the traffic levels are higher than normal already. It's at 20%. The next week is even higher. You can also see very nicely the weekend distribution and the weekday distribution. The weekends are pretty normal, but the weekdays are high, right? The internet pretty much absorbed this extra load without a big problem. And the reason for that is most of the internet is already on CDN technology. And because the CDNs have this large set of edge servers, they're able to absorb any sort of flash crowds of demand. Okay, so I want to talk a little bit about CDN research. There's lots of interesting science that goes into CDNs. I talked about building the GPS of the internet. That's a very cool problem all by itself. You need to get information from everywhere in the internet efficiently. Then you need to figure out algorithms that can actually do the routing. That's interesting. I talked about balancing the load. When there's a flash crowd, how do you balance the load, right? There are very interesting algorithms that can do that. There are lots and lots of algorithmic and systems problems in CDNs. And I just took the liberty to look at the papers that we've written on CDNs. Maybe this is a little embarrassing, but we've written something like 36 papers over the last 20 years. The very first CDN paper is 2002. We didn't write the paper immediately because we were building it, and we wrote it later. And then we've been continuing to do research on CDNs ever since. It's a really rich area for science. But I want to actually point out something slightly different. When we started to build CDNs, a lot of the science was already there. What we really did was, take pieces from different places and put them together. And I think about this in the context of people questioning research funded by the federal government. People sometimes say, no, why do you need to fund research by the federal government? Why do you need to fund, blue sky research, and so on and so forth, right? The answer simply is that when we actually build something practical that everybody uses, like streaming or teleconferencing, the science that goes under the covers is 50, 60 years of research. And a lot of this research was not even done in the context of the internet or done in the context of CDNs. I've named a lot of things here, like consistent hashing, Bloom filters. I like to talk about stable matching. The work for stable matching was done in the early 70s, and the context of that was matching students with colleges. Students have preference for colleges, and colleges have preference for students. How do you make both sides satisfied? That was it. But when we started to build CDNs, we came across a similar problem, which is you have users, and they have preference to which servers they want to connect with. They like servers that are faster. And the servers have preferences on which users they want to serve based on cost. And so we looked at it and we said, we all came from a theory background. We looked at it and said, well, this is exactly stable matching. And so it turns out that CDNs do the largest stable matching problem in the world every 20 seconds. So I wanted to point this out mainly because it's really important to fund basic research, and it's really important to have federal funding for this research. Because all the good things, applied things that come after it, sits on top of these kind of things. Okay, all right. I said I would talk about three things. I think I talked about faster, and now I'm going to talk about smarter. Okay? What do I mean by smarter? I'm going to talk about edge computing and edge AI. Okay, so I want to tell a little bit about edge computing. Back in the day when we were building CDNs, people used to ask us, what are you thinking about next? Are you kind of a one-trick pony and this is all you'll do? And we always used to say, we push content to the edge close to users. It also makes sense to push compute to the edge close to users, for really the same reasons. So if you think about this picture here, content delivery took the content from an online service and pushed it to the edge, right? And edge computing is taking the compute and the data and pushing it to the edge. So we built the first edge computing service. In fact, we coined the name for it. And also, that service actually used it as a trademark for many years. And the reason to do edge computing is really the same as the reason to do content delivery. If you want to do compute faster, more reliable, and more scalable, it makes sense to push it close to the users. Okay. The early, there is such a thing as something being built too early. And I think that was certainly the case with edge computing. Most of the applications in the early days of edge computing were very simple things like, you can configure your phone, you can have your shopping cart run on the edge close to you, you can locate who's the closest Chevy dealer, things like that, very simple applications. And for a long time, it played backfiddle to CDNs. But the last 3 or 4 years, that has completely changed. Because we found an important kind of computation that needs to be done close to users. And that is nothing but AI. So when AI has come into pretty much every online transaction that we do, as we go along, every online transaction that you do is going to involve AI of some sort. And the computation for AI needs to happen somewhere close to the user. And it needs to be also fast. It needs to be scalable because it's not one person accessing AI. It's going to be a billion people. And so what we really need is something like a content delivery network, but it's not delivering you videos or content. It is delivering you machine learning inference, right? And so this is the picture that's evolving. And this is something that we are spending a lot of time researching. How do you really do edge AI where you're able to serve AI to billions of people? And this is an example of where you could do edge AI. This is an AI-powered voice assistant where you're just talking to your car instead of like punching your address and saying, GPS, take me there. You're just talking to your car. You're saying, I want to find a place, a grocery store that sells this product. I don't want to travel more than 10 minutes. Can you plan something for me? Right? How do you build something like this? You need this AI to be running close to you on an edge somewhere. And so this is a very good example of edge AI where you need fast response times because you're talking to, you're conversing. You want the response times to be quick, and you want to do computation, close to the user, so that you can actually do this, right? And I should say that this is a case where the imagination of the world has overtaken what we can do on the science side. So every time I talk to people, they come up with interesting uses for edge AI. So I just listed a few. Conversational web. People don't want to click on the web anymore. People don't want to type things in search anymore. They just want to treat it like an agent. They just want to ask something and talk to your browser, so to speak, right? How do you really do that? You need to have AI running close to the user to be able to do that. Personalizations and recommendations, that's an obvious case where you need something to learn what the user is doing and do the right thing. AI-powered content generation is another thing where you want it to generate images and videos. Real-time video understanding is when you want to ingest video and you want to understand what is going on, and you're ingesting it at the edge, and you need some compute there to actually figure it out. Fraud detection is actually a very interesting one. You go to your bank and you're transacting with the bank, right? You're talking to an edge server of a CDN to transact with the bank. And you want to find out immediately if there is something fraudulent going on. What happens today is that they analyze it, and after one day, they say, well, there's something fraudulent going on. But you want to do it immediately. So what you need is, on the edge, you want some compute running. You need to have some kind of machine learning running, which is looking at your access patterns and trying to figure out if this transaction is fraudulent or not. Physical AI is, of course, one of the more harder things. It has to do with robotics and controlling robots. I say it's harder because the latency guarantees need to be really hard. Okay, so this is what's happening. The smarter internet is happening. It's happening at some amazing pace. The imagination is actually ahead of what the science can do. But it also brings a lot of interesting problems. Once you have AI running on the edge, that AI can be attacked in so many other ways. As you know, you can do things like prompt injection attacks. You can ask the AI something and try to kind of reveal personalized information. You can have AI spit out toxic output, and you don't want to be responsible for that. And then you can do things like AI denial of service, where you can make the AI do so much work that the edge server has no resources to do anything else. So there's a whole new range of attacks and guardrails that come into play when you think about running AI on the edge. Okay. Now I want to switch gears and talk about the third thing that I said I would talk about, which is how do you create a greener internet? And I'll tell you in a minute why I'm actually most worried about this part. If you know anything about the internet, you know that every chart that you show about the internet is always growing exponentially, right? This is traffic on the internet, on the edge. This is the COVID bump. It might seem like a bump, but then you see it just keeps rising, right? The amount of traffic on the internet, there are more users, and each user is downloading more stuff. There are more applications, and that's just going up through the roof. And as I said, edge computing has just caught fire. For like 20 years, it was really nothing. But if you look at some of the projections based on AI, people have projected that it would be, in another 10 years, it would be worth $330 billion, right? It's like a tenfold increase, right? What does all this mean? If edge servers are going to be doing more and more work, more computation, more bits, they take a lot of energy, right? And this is really the most difficult question, is that having AI ramp up so quickly means that you need to have big, large edge servers. You need to have big deployments of cloud data centers, right? And not only they take up a lot of power, a lot of energy, first of all, right? They emit a lot of carbon, unless it's all renewable. And they also consume a lot of water for cooling. So all of these things impact the environment. In fact, we wrote this paper in Communications at ACM a few months ago, how the effects of all of this could be inequitable. For example, Arizona has a lot of renewables, but it also has very little water. So if you go in and put lots of data centers there, you're going to have a problem with water. So it's a very complicated problem. So we've been thinking about some ideas for solving this problem, and I'll just mention three. One idea is that the edge servers are numerous. And so we can actually figure out which edge servers have renewable energy and which don't. So the servers are being powered by electricity, and the electricity is being generated in different means. If you generate it using hydroelectric power, then it doesn't have any carbon in it. If you generate it using coal, there's a lot more carbon in it. If you use solar, there's no carbon in it. So we actually built a tool called CarbonCast, which can actually predict how much carbon is in the electricity that's coming out of your socket. And using that, we can actually think about how we can move workload from servers that have more carbon to servers that have less carbon. So this is something that we are actively looking at. Here is another idea. One of the problems with really large data centers is that it takes a lot to power them. Right? For example, a traditional data center, a 100 megawatt data center, requires 450 acres of solar to power them. So a different option would be to have really, really, really small sets of servers. We call them micro edges. And this is an example of a micro edge, and that's an example of a micro edge. Right? It has only a few servers. And they can be powered by renewables, because you can have a solar on the roof of it, or there's been proposals of taking every windmill in Scotland and deploying a micro edge there. You need, of course, batteries, because the renewable energy is not going to be available all the time. So this is a different kind of architecture for the edge, where you don't have thousands of data centers. You have like tens of thousands of edges. And how do you actually deal with that kind of a distributed system is something that is very interesting, and we're looking at it. And finally, this is probably the most zaniest idea that we've had, is we now have LEO satellites orbiting the Earth, like Starlink. And we've been exploring if we can take the CDN edges and put them in those satellites. Okay, so you take your CDN edge servers and then put them in the satellite. The odd thing about that is that the edge is moving away from you all the time, right? It's over Amherst, and then it's over Mexico in a few minutes. So how do you really even cache content in such a situation, right? Those are the problems that we've tried to solve, where if you take the edges and put it in the satellites that are moving, right? How do you actually build a CDN from that? And we have some initial ideas that we published last year. And why is this related to sustainability? The thing about putting it up there in space is that there's plenty of solar, right? And cooling is not a problem because it's already cold out there. So it solves a lot of the problems we have with cooling and energy. And so this is actually something that we've been exploring. I want to really end with this statement here. So I've kind of sketched very briefly sort of the internet of the 90s, how we were able to make it faster, how we could make it sustainable. The thing that worries me most here is that I feel like the internet has a lot of great potential in the future, especially with things like Edge AI. But it's also very worrisome because anything on the internet grows at some amazing exponential rate. How to make that sustainable, I think, is really the biggest problem. And so with that, I would like to thank everyone who's here. I would like to thank UMass as an institution because it's been my home for many decades. The administration has always been extremely helpful. When I wanted to be away, for example, they said, "Oh, yeah, go ahead, go out there." And really, it's been really good. I mean, I really love working with the students here, and I've really had a really great time. And thank you very much.
Thank you. I will let you, you're great teachers, I'll let you conduct your Q&A.
Okay.
And our colleagues will have mics available for everyone. And then we'll wait for people who give us instructions to maybe give a minute when we're ready to bring in the chancellor. Is that okay? So, but I'll open it up for questions.
Sure.
Please.
That last piece you had up there with the satellites, seems to be a lot of problems with that, I would think. The bandwidth getting down to the Earth, the solar storms, and the rockets to take the stuff up there, and what environmental effects that would have.
Right, that's a great question. The question is, let me just repeat the question. The question is, the satellites have a lot of issues with solar storms and bandwidth. Solar storms is actually a problem because things could shift in orbit because of the solar storms. But we actually, as long as they can find their neighbors, so these satellites have neighbors. They're in different orbits, but they have neighbors. We made sure that some of our protocols would work even in that case. And in terms of the bandwidth, that's always going to be limited. But we are actually thinking about ways in which you can conserve that bandwidth so that we don't waste it. But the bandwidth is going to be an issue. So it's not clear that you can do any kind of content from there. You may not be able to do HD videos from there, but you can certainly do things like machine learning inference where the amount of traffic itself is not that much, but you need a lot of compute. So it's not going to be the right solution for everything, but it can be for some.
How do you repair it?
I would let Starlink deal with that, I would say.
Thank you. This is a wonderful talk. How do you choose which content gets archived at which edge location?
Okay, so that's a great question. The question is, how do you decide which content gets archived at which location? We don't try to decide that. So the first time you actually download something, we do pull it from somewhere else. But then after that, we use some policies like least recently used. If something, the short answer is, if something is popular and gets used a lot, it will be in the local server. But as you know, the content in the world is infinite. So I can't store everything in the UMass Edge. Only the things that are most likely to be used. And we have algorithms that can figure out what set of content must be stored depending on what people are accessing.
You said that this is research that has been going for 60 years. And it has changed the world. And we've seen faculty members in your department that have done that consistently. where is the application of that research starting to be faster? Or is there something that you can see now that is we're going to be talking about 60 years from now that it is a change? And I'm trying to, because we have students here, and sometimes I've heard them even said it myself, it's like, well, everything I could do has been invented, or everything I wanted to create in macroeconomics has been studied. So what is, if you can give us a little bit of a glimpse into the future, you talked about the satellites, but you talk about how quantum could emerge into this. Just, can you inspire some of our students who are here in the audience with that?
Absolutely. So I think the place that's actually growing at such a major pace and is most likely to completely change what the internet looks and feels like is that last part, the part that I talked about, the intelligent edge. So the way in which we've been communicating with the internet will be much more agentic, that we won't be clicking and browsing and things like that. We would be interacting with it more like we would with an agent or a human. And that is a very big change for the internet. It is still the internet under the covers, but your experience, the human experience of accessing the network will be completely, entirely different. And I see that as changing really, really quickly. And even 10 years from now, looking back, we might be thinking, what were those people doing with the mouse and all these other things? If you talk to people in the venture capitalists and other folks out there, they're already talking as if this is already there. But from as a scientist, from the science point of view, I look at it and say, not quite. There's still a lot of science to be invented before that happens. But I see that happening. That will completely change the way we think of these networks.
So when Akamai came in and revolutionized content design, there was a global optimum there. Basically, everybody was better off getting things where they wanted to go. And about the same time, there was this innovative idea to take the electricity system and optimize it, and that was Enron. I'm wondering, how do you get the good outcome or the bad outcome? From how do you design a system to make that work?
Can you repeat that last part? What about the electricity system?
Say again?
Can you just repeat the last part about the electricity system?
Well, you're putting in a system to manage some enormously complicated situation.
Right.
And how is that going to be done in a way that it's going to be somewhere socially responsible? Whereas Enron being the bad example.
That is a great question, and that question again surfaces a lot when we think about Edge AI. Because the people who are benefiting from Edge AI are not the people who are being impacted by the pollution, by the water shortage, by the higher electricity bills. People are already talking about, the AI data centers are making my electricity bill higher. So I think trying to figure that out in the context of Edge AI and cloud AI in general, I think is a really, really important problem. And this is the thing I worry about most, that the benefits of, so far the benefits of the internet have been relatively even, but I mean, that's also very arguable. Because a lot of places don't even have the internet. But that disparity is going to get even worse with Edge AI because the amount of resources that you need for something like that is enormous, and the environmental impact of that is also enormous. And it's also pretty clear already that the people who actually are impacted are not necessarily the people who are going to benefit from it. So, but that's a great question. I think that's kind of what we should be thinking about as scientists.
Did someone over here have a question?
Thank you. I enjoyed the talk. There's a lot of discussion these days about whether AI needs guardrails and what form that would take. Is that regulation? How does AI on the edge complicate that?
So AI on the edge absolutely needs guardrails. In fact, I had that on the slide, some examples. Because if you really want to deploy AI on the edge, it has to comply with all sorts of different things, right? So for example, if you have an edge in Europe that's giving out answers, it has to comply with EU law. It cannot be doing something abusive. I had an example where an AI sold a car for $1. And if you have to stick to that and actually sell it for $1, that's a huge loss. So that's really like the biggest problem, whether it's the AI is in the cloud or in the edge, building guardrails around it. And the guardrails have to work in real time, right? It can't be the case that you say, wait a minute, I'll take 5 minutes to give you the answer, right? It has to work in real time. And that's really a very hard scientific problem.
We have one more.
So the solutions you presented for sustainability at the end of the talk seemingly focus more on content delivery networks and I guess networking in general. But there's also other ways people are trying to attack the problem with more energy efficient compute and different ways to generate energy. What issues do you think are the main ones we need to solve to kind of achieve sustainability, and how do you think the solutions you presented mesh together with them?
Right. So sustainability is such a large problem that there are many different pieces to this puzzle, right? Certainly, we need to figure out energy generation, energy storage. We need to figure out how to distribute the energy. The grid right now is not, it cannot sustain this expansion. I spoke about a very narrow sliver, which is really on the computation and internet, edge computing and edge delivery side of things. But all of these solutions need to creatively come together to really create a comprehensive solution. And they all interact with each other as well.
Good, if you can help me. Thank you, Professor Sitaraman. If you can take your seat just for a few minutes. Very good, and please don't take away this slide because it's the basis of all my talk today. So I just want to say again, Professor Sitaraman, thank you very much for your enlightening lecture today. I have to say that I was asked today what makes UMass unique. I was asked why would the students come to UMass? What is the faculty doing? What is the approach that is very unique to us? And this slide emphasized the point that I tried to make, perhaps not as eloquently as you make it in this slide, which is every faculty member, whether it's in the sciences or it's in the cultural side or it's in the art side, in the creatives, they're trying to address a challenge or a social problem, trying to ensure that as a university we provide access with equity, we provide with inclusivity, we address it responsibly. And what you said here today, as a scientist, we bear a special responsibility to shape which of those futures prevails, because we're taking this as extraordinary promise, but with extraordinary risks. I can tell that that is what makes UMass unique. And I have, after what I was asked today and tried to put it together, and then seeing you say it out loud, and having base your career and addressing these kinds of issues, emphasize why you felt so at home at UMass and why you have contributed so much to this university. Because clearly you're vibing in the same way as what we have on this campus. I just want to say thank you. Thank you for emphasizing the point. Thank you for addressing the risks and taking that responsibility to make the internet better, but also safer and also greener. So thank you very much for emphasizing that. And now it is my pleasure. I get to do things as chancellor of this university that are truly pleasures, and these are sometimes really sort of personal moments, to be able to bestow on someone and present someone the highest honor that this university has. It's truly, truly a pleasure to get the opportunity to do that. But I know that I do that on behalf of the whole university and all the university community. It's not just, is the chancellor medal, yes, but it represents every student, every faculty member, every staff member, every alumni member, Everyone who is affiliated with this university recognizes what you bring to the table, recognizes the impact of your work, and we want to elevate you and celebrate you as I present to you the Chancellor Medal. Thank you very much, Professor Sitaraman. If you can join me up here. Thank you very much.